Welcome to Lee Springs Training Program. This program will cover various aspects related to spring principles and design. In this series, we will cover the most popular type of spring, the compression spring. In Module 1 of our series, you will learn about what a spring is, principles of spring design, spring rates, the primary elements of spring design, the process known as spring setting, and compression-type springs. Now, let's get started. To understand springs, it helps to understand what a spring is. A spring is essentially a mechanical object that deforms when acted upon by an external force, and then returns to its original shape when the external force is removed. Each spring design has a unique function, and in the case of the compression spring, the primary function is to push. Now some basic principles of spring design. There is a principle of spring design known as Hooke's law, which relates to load and deflection. Essentially, Hooke's law states that a restoring force due to a spring is proportional to the distance the spring is deflected and acts in the opposite direction. Another important principle related to spring design is spring rate. The spring rate is the ratio of force per unit of deflection. Let's take a further look at spring rates now. Spring rate is a change of load or force per unit deflection as the spring is compressed. As an example, spring rate may be specified as the amount of force to move a spring 1 inch. A standard helical compression spring has a spring rate that is essentially linear over most of the operating range. The first and last few percent of the spring's deflection has a nonlinear rate. When a spring reaches solid height, the spring coils are at a stop against each other. When talking about spring rates, this is generally the spring rate between 20% and 80% of available deflection. Now let's take a look at some of the design elements related to compression springs. One primary design element is the direction of wind. A coil spring can be wound in either a left-hand or right-hand direction, similar to a screw-type thread. A left-hand wound spring will spiral in the same direction as a left-hand threaded screw. A right-hand wound spring will spiral in the same direction as a right-hand threaded screw. Direction of spring wind can be important depending on how the spring is used. To determine the best wind direction, consider the application. For example, coil wind is important when you have one spring working inside of another. To keep the springs from binding against one another, the wind of the inner spring and the outer spring should be in opposite directions. If a spring screws into a threaded component, match the direction of wind to the direction of threads. Now that we have looked at how the spring is wound, let's take a look at other design elements. Spring squareness. Spring squareness is defined as the angular difference between the outermost limit of a spring diameter when compared to a straight edge at the right angle to a horizontal flat plate on which the spring is standing. Spring parallelism relates to the ends of the spring and how parallel they are to one another. Now let's take a look at the physical dimensions of the spring, specifically spring diameter. Spring diameter is often referenced in a couple of different ways. One method is the outside diameter, or OD. This dimension is important when the spring is used within a cavity. Another dimension is the inside diameter, or ID. This dimension is important for springs that work over a rod or shaft. The next type of diameter is the mean diameter, which is most often used for calculations for stress and deflection. Free length is the overall spring length in the free or unloaded position. If definite loads are specified, the free length should be an approximate dimension, which may be varied to meet the load requirements. Spring index is defined as the ratio of the mean diameter to the wire diameter. A high index spring would have a smaller wire diameter and a higher spring diameter, similar to a light pressure spring. A low index spring would have a larger wire diameter and a lower spring diameter, similar to a hefty spring. Load is the force required to compress a spring to a specific height, rather than the amount of force to move the spring a specific unit, like spring rate. Load differs from spring rate in that spring rate is the amount of force to move the spring in increments, where load is the amount of force to move the spring to a specific height. Another important element is a spring's solid height. The solid height is a dimension of a spring when all the coils are closed. This dimension, if critical to an application, should be specified as a maximum dimension. The number of coils should be specified as a reference figure and should be stated whether it refers to the total coils, which includes all coils including those which are used to form the ends and may not deflect under load, or the active coils, which are those coils which are free to deflect under load. Pitch is a dimension related to the distance between the centers of adjacent coils. Now we will look at what physically happens to a compression spring after manufacturing. Prior to the first compression, a spring's free height may be longer than the specified height. This is common during the manufacture of springs and can be compensated for in two ways. A spring can be built with free length which has an allowance for set. This involves compensating for the length loss when a spring is fully compressed for the very first time. Another method is known as removing the set, also known as presetting or a set spring. This is an additional manufacturing step that may be done to ensure that the spring is at the correct free height for use. This process is done by compressing the spring to the solid height. A set spring's new free length will now be stable and consistent throughout the future compression cycles. Now let's take a look at spring ends. This first spring has a closed end, where the end coil's pitch is reduced so the end coils touch. The next spring has an open end, where the coils are consistent with no pitch change through the end of the spring. Another end type for compression springs are the not ground type and ground type. As you will notice, the ground end type spring is ground flat, where the not ground type has a less parallel end. Compression springs can come in any variety of shapes. Custom designs may have any number of shapes depending on the application. Some common custom shapes include the cone shape, where the spring radius decreases. This is common for a battery spring. An hourglass shape tapers tighter toward the center, and the outer coils have a larger diameter. The barrel shape is reduced at the ends and wider in the center. The reduced end spring is straight across the center coils and tapers only toward the end coils. There are some other compression springs to be aware of that are available. The Hefty series, which are die springs ideal for high stress, heavy load applications. The Redux Wave spring. These springs are spotlighted in detail in another presentation, but essentially, this design is excellent in applications where the space is critical. This unique design generally occupies 30% to 50% of the compressed height of a conventional round wire spring. The light pressure spring. These springs are suitable for applications requiring low spring rates and low pressure. Lee Spring carries a wide range of stock springs and has engineers available to support custom designs. No matter what your spring needs are, you can count on Lee Spring to provide you with the highest level of customer service and engineering support. If you would like to learn more, view our other spring knowledge sessions, refer to our catalog, visit us online at www.leespring.com, or call us at 888-SPRINGS.